Hello and good afternoon, scholars. Mr. Sniffen back here with you with geometry class for today. It's a beautiful June 2nd, and it's also my birthday, which is awesome to be able to spend with you guys today. Just want to get started off first with something slightly different in terms of our class. What I like to do is take a look at what we would call like our class norms in the virtual space. Just some good things to go over with you if it haven't been pressed upon you already is that when we're taking a look at these videos, my expectation is for you to be taking notes, obviously. To do that in the best way fashion though is using things like paper. I find that to be much more effective than taking notes on say like a Google Docs and switching back and forth with Edpuzzle. Plus it's not pausing everything all the time when you're switching back and forth. In addition to that, please use a pencil, way better than a pen in terms of math class in my opinion, but also something like a straight edge, particularly in this last three-dimensional unit, because we're going to be doing lots of drawing. And if you can somehow avoid your little brother or sister or your parents, please try and find a quiet learning environment, the best you can, at least for now. What I'd like to do today is go over just some comparisons in the content that we've talked about recently. Previously, last week, we spoke about this notion or this concept of volume, and we described volume basically as the physical space objects take up, or what we would do or say is the measurement of three-dimensional objects. The amount of height or the base, the width, the length, all these different ideas we took apart last week and tried to relate them to math, essentially, or to our geometry course. The example that we had previously was primarily associated with this idea of a cylinder or a rectangular prism. Here we have, once again, the GeoGebra website open, and we have what we would call a rectangular prism. Prism in that we have a congruent bottom and top base and connect it with parallelograms. It's a 3D box, if you will. The big notion that we took away from the previous lesson, say lesson 10.2, our cross-section section, is that we have this idea of planes interacting with our objects. With things like cylinders and prisms, what made them unique was that as our plane moved up and down in terms of the horizontal sense, our objects remained the same. Our cross-section, that slice, that piece we cut out, was ever consistent. We call that a constant cross-section. So when we were taking apart a box or a cup, every time we sliced across, the cross-section or that orange section here was congruent. However, this is not the case in all objects. We saw that in our Nintendo example that we were able to just stack cartridges essentially and multiply them, that base cartridge, multiplying that value times the number of cartridges we stacked, which is called our height, gave us our volume. But what happens if we have an object, say, like a pyramid? Pyramids are a little bit different in terms of their definitions, obviously, and their visual sense. We have a base of some sort, two-dimensional base. In this particular example, we have a hexagon, and we have triangles connecting up to a vertex, a single vertex. But what you'll see in this particular example here is we have a plane once again, but as we slide it down, creating all these different horizontal planes, we notice that the base is getting larger. In comparison to our real-world example, that would be like if we were stacking up those Nintendo cartridges and they were getting infinitely smaller until we reach a top vertex. If that's true, or if this example is correct, that means we can't use the same volume equation. Once we get to the top, we're no longer stacking that same unit of measurement. We're in fact stacking something considerably smaller. Therefore, we can't use that equation of just base times height. We're not just repeating the same object, we're repeating something different, if you will. To calculate a pyramid's slightly different. Our equation is essentially our base times our height once again. In this particular example, we would use our equation for finding a pentagon bottom and then multiplying it out times our height. If we had a square base, we would take our square value, length times width, multiply it times our height. But with pyramids, we're going to do that calculation, but we're going to multiply it by 1/3. What mathematicians found back in the day, we're talking thousands and thousands of years ago, dating back to the ancient Egyptians even, if you will, that pyramid calculations are different. They found that if they were to take things like cones, say, or like a pyramid in this particular example, if we were to fill up that object, it's going to take up about 1/3 the amount of space in comparison to, say, just a pentagonal prism. We took this particular object here, treated it like a prism, and just continuously stacked those pentagons up on top of each other. The pyramid version of that is going to be about 1/3 in size. So this consistently happens no matter the type of pyramid, whether that be a right pyramid where the vertex is concentric, it sits directly in the middle, or if we have what's called an oblique pyramid, where our vertex sits slightly shifted off to the side. This ratio of 1/3 times the base times the height is always going to give us our calculation for volume. What I'd like to do now is show you how this gets represented numerically or algebraically in our class. Let's begin to go ahead and look at how we calculate these values out. First thing that we'll need is an actual diagram to look at to get our values. And what I'd like to do is kind of show you how to draw that rectangular prism. First thing, I'm going to show you an example here. This is what we're going to be looking for. Essentially, our base is going to be a rectangle because we note it with 4 right angles. But since we're drawing an object or a 2D object and trying to turn it into something 3-dimensional with depth, we're going to kind of squish it a little bit and turn it slightly into a parallelogram so we can look like we're moving out away from the viewer. To do this, we're going to use our trusty compass, and I'm going to use the blue lines here to try and set myself up nice and neat. What I'm going to do is have this forward line that's here have a little bit of length to it. So this first diagonal I'm going to do as so. What I want to do next is this other portion of my rectangle, I'm going to have it, the angle that we're looking at, it's not going to be too big. Smaller side. We're going to go over now. We're going to go over here and we're going to try and connect this in what would be slightly a parallel line. So I'm just going to shift over my ruler using kind of the same angle. And then I'm going to go ahead and connect off. It's slightly off. It's okay. What we're going to do is we're going to do here, sorry kitty, is try and draw our vertex or the top portion of our pyramid now. What we're going to try and do is find a spot that's near the center of our image, and we're going to have it slightly shifted towards the center. We're going to avoid this spot here. We're going to try and avoid creating lines directly up. One of the things that can occasionally help here is that if you have multiple lines or multiple layers to kind of show the 3-dimensional portion. I'll show you what that looks like right now. I'm going to draw an imaginary line going up. I'm going to make my spot here. This is going to be an indication that we have our altitude because it's going to be a right line going up here in a moment. I'm now going to connect my points. This portion, this front portion, the front of our pyramid, we're going to use solid lines. That's going to indicate that that object is in the foreground, as in like it's the physical side that we're seeing. We use the dotted lines typically in diagrams to show portions that we can't see. This bottom right-hand side of the triangle we're going to see. This front section we're going to be able to see, and this back is going to be technically invisible, and we're going to use just the dotted lines. So here we have what we can kind of describe as a rectangular pyramid. We have single vertex on the top. We have a base that we can measure. This particular base that we're going to measure is going to be a rectangle. So what we're going to go ahead and say is, to solve for the value of our base, we're going to do 11 times, say, 9. And that's going to be a value of 99. The next thing we want to do is go ahead and look at what our height is going to be. Oftentimes you'll see in your diagram like an arrow pointing out to that center altitude line, and then we're going to say we have a measure of, say, 10. Okay, next thing that we're going to do is we're going to take that base value of 99. We're going to then go ahead and multiply it by the height of our object, which is our value of 10. Combined out, we get a total of 990. We now need to incorporate this notion that we're missing portions of our theoretical rectangular prism. Once again, the pyramid is going to be 1/3 the size of that normal rectangular prism, because we have these slides cut off and ejected off in the 3-dimensional space. And what we're going to do is multiply times that consistent value of 1/3, and we'll get a final solution of 330. Let's say we're looking at centimeters, 330 centimeters, and of course it's cubed since we're looking at something that is 3-dimensional. Get our final answer of 330. This is how we calculate it out with a pyramid. The same thing happens with a cone in that we have a 1/3 size. What I'd like to do is show you just 2 more geometric examples, or something that might be similar to your independent practice, to kind of give you a nice visual example here. So let's take a look for number 2. In number 2, I'm going to attempt to draw what we would say is something like a triangular based pyramid. Remember, with a pyramid, the base doesn't have to be this really simple shape like just a right triangle or a square or rectangle. It can be also things like hexagons or pentagons, and we just have to continue using that notion of base, whatever the base is, times the height, times 1/3. But in this example, I'm going to use just a right triangle because they're a little bit easier to draw out. I'm going to have something that's going to be about 90 degrees here in the corner. And of course, with practice, it's always going to make these things a little bit better to draw out. So I have my right triangle here. What I'm going to now do is, as the observer, I'm going to be looking directly from this direction, and I'm going to swoop up my vertex to what we would probably call 90 degrees from here. And I'm going to put a little dot there. I can mark down this notion of height and connect with my solid lines for my foreground. And in this particular example, we're going to be able to see coming off this side as well too. And we now have what I would say is a pretty well drawn pyramid. Alright, so to go ahead and calculate our values, what we're going to do is I'm going to label these out here for you. We're going to say this short side is 3, this longer side is 4. Our height, we're going to also go with a value of 4 centimeters as well. Since we have a base of a triangle, what is our triangle equation for the area of the base? If you remember, for these particular examples, we're doing base times height times 1/2, and that's going to give us that proportionality for the area of a triangle. In this particular triangle that we have set up here, since it's a right triangle, we can quantify this value right here as our base, or the bottom portion of the triangle, bottom portion. And since it's a right triangle, we already have that altitude or that height already listed for us as 4. So go ahead, do 1/2 times 3 times 4, and that's going to give us 12 to 6 centimeters. We can say squared if we want to. The next thing that we're going to do is now multiply by the height. Our height, which we saw, is going to have a value of 4. We do 6 times 4, which is 24. We multiply that value by 1/2 because we're gaining that balance where our cross sections are continuously getting smaller as we go up towards the vertex. And we get a final answer of 8 centimeters cubed. So not too bad. Additional step beyond what we saw with our triangular prism or our rectangular prism, where we did just base times height or length times width times height. In the pyramid, we have to add that 1/3 value. Lastly, for example number 3 here, if we're going to look for a cone as our 3-dimensional object, we're going to have to draw it kind of similar to the cylinder, where we're going to be using some type of oval shape along the bottom. And I find it just using long kind of like swooping arcs to connect everything helps out a bit. Next thing that we're going to do to complete this ice cream cone looking shape, I'm going to put a vertex on the top. Try and draw it out from what you would say is the diameter of the figure. Diameter would always be represented with dashes, and typically a point where it might say, like, say, circle O, for instance. But here, we have a height indication, and we're going to kind of do the same thing once again. We're going to take our base value, what's the base value in a circle? Our base value is going to be the same thing as if we're going to go ahead and solve for our area. Solving for the area of a circle, we're talking about that equation of pi r squared. In our diagram here, let's go ahead and say our r value today is going to be, we'll go with, see here, we'll say 6. 6 is going to work well. We'll go with 6, and we'll say our height here is going to be a value of, let's go with 3. Okay, so to do our equation here, pi times 6 squared, which gives us 36. We're going to multiply that value once again by our height. We're going to do times 3, which is a value of 108. 36 times 3, our base times our height. We're then going to multiply that value of 1/3 again, that proportionality statement, and we're going to go back to 36 centimeters cubed. So for these equations, what we're looking once again to do is we're taking our base, we're multiplying it by the height, and since our pyramids, our cones, do not have that constant cross-section, we have to take that in consideration, and that proportionality statement that we end up getting is consistently a value of 1/3. So it's our base times our height times 1/3 gives us our. To finish up for today, just as a reminder, the reason why we have two different equations all has to do with the cross sections. Solving for the volume of something like a rectangular prism allows us to calculate the base and multiply it by the height, because that base has a consistent cross section as it goes up and up and up, just like the Super Nintendo cartridges. However, when we looked at the pyramid, particularly on that GeoGebra example, we saw how the cross section progressively got smaller as it got higher up towards the vertex of the cone and the pyramid. To take this into consideration, we had to then multiply that original base and height by 1/3 to consider what's being removed in that negative space from the object. Lastly, just as a reminder, today we're going to have office hours. Please come by, say hi, it's my birthday today. I'd love to hear from all of you just to go over some stuff and celebrate with you. But until next time, you need anything, have any questions, please make sure to reach out via email. Hit me up with those messages if you have anything late. Just as always, be specific in terms of what assignments you're missing. But besides that, I hope all of you have a super nice day. Bye.